Welcome back to the McMaster University course, Computing and Software 701, Logic and Discrete Mathematics. Last time we started on the topic of basic mathematical concepts. We looked at what is mathematics. In particular, we talked about how mathematics is a process that involves the creation and exploration of mathematical models. And there's various ways of exploring these models. The models are built up from mathematical structures, and the mathematical structures are built up from mathematical values. Then we looked over some of the basic ideas about mathematical proof, and now we're ready to start looking at a whole variety of different kinds of mathematical values. We're going to start with numbers. Now, numbers are mathematical values that are part of number systems. So what is a number system? A number system is a set of mathematical values called numbers, and there's also a set of functions on these numbers which are called arithmetic operations. And pretty much every number system has the operations of addition and multiplication, but they may have other operations as well, like subtraction, division, and exponentiation. It's important to keep in mind that a number system is not the same as a numeral system. A numeral system is a system for writing down expressions that refer to numbers, like the Hindu-Arabic system that we use today, or like the Roman numeral system that was used in Europe until the last few hundred years. So let's think about some common number systems. I'm sure almost all of you have heard of all of these. We have the natural numbers, which are 0, 1, 2, 3, 4, and so forth. This is a system for counting and ordering. It's probably worth pointing out, sometimes people do not include 0 as a natural number. Those are people who think we don't need 0 for counting. We start always counting with 1 and 2. We don't really need 0. Usually in mathematics, or often in mathematics, the natural numbers does not include 0. But in computing and in logic, it almost always includes 0. And some pedantic computer scientists and logicians like to count. They like to count starting at 0. So for instance, if I had three things here, A, B, and C, they would count like this. They'd say 0, 1, 2. There are three things there. But we're always going to keep 0 as a natural number. Okay, so those are the natural numbers. The integers are an extension of the natural numbers, and it allows us to count both backwards and forwards. The rationals, here, these are the rationals. This is integers, by the way. The integers are named by the Blackboard Z, or Z. Blackboard Z or Z stands for Zahl in German. And Blackboard Q is the rational numbers. These are the numbers for measuring. And then we have the reals, Blackboard R, which are the real numbers. These are used for solving geometric problems. We have the complex numbers, which is denoted by Blackboard C. These are for solving algebraic problems. We also have a set of numbers called Zn, where n can be any natural number greater than or equal to 1. These are the modular integers, and they're used for doing clock arithmetic. So let me try to describe how clock arithmetic works in case you don't know. So let's say I have Z5. So Z5, I'm going to have 5 numbers, and I'm going to use the numerals from 0, 1, 2, 3, and 4. Those are the 5 numbers. I've written them in the clock form. And if I'm going to count, let's say I'm going to count to 6, I start here, I go 1, 2, 3, 4, 5, 6. The answer then is 1. It's basically what I do is I take 6, I divide it by 5, and whatever remainder I get, that's the number. If I'm going to add, I do something similar. If I'm going to add, let's say 3 and 4, I go 1, 2, 3, 1, 2, 3, 4. I get 2. So I have 3 plus 4. And I divide by 5. And the remainder is going to be 2. So that's how clock arithmetic works. It's you find it all throughout mathematics and computing. We're going to see an example of it near the end of this lecture. Okay, so I've cleaned up my board here. Let's go back to here. Maybe I'll clean this up too. And so it's important to note that the natural numbers are included in the integers are included in the rationals are included in the reals, and reals are included in the complex numbers. And the modular integers are included in the natural numbers for all n. Okay, so these are the common number system, but there's some other less common but very notable systems. There are the ordinals. These are for ordering infinite sets. I'll give some examples of these. There's the hyperreal numbers. This is an extension of the reals. And these are for calculating limits in calculus. The hyperreals were the basis for calculus that was used by the founders of calculus, Leibniz and Newton. Leibniz in particular described how the hyperreal numbers worked, and it took until the 1960s work by Abraham Robinson to show that the hyperreal numbers really do make sense. We really can use them to do calculus just as well as using the definition of limit, which is popular now in calculus. We also have here the Gaussian integers and the Gaussian rationals. So the Gaussian integer is, they have the form, I take an integer and then I add an integer times I. So a and b are integers. I is a symbol which denotes the square root of -1. It's the imaginary number. So we can see here that Gaussian integers is a subset of Gaussian rationals, which is a subset of what we could call Gaussian reals, but the Gaussian reals are usually called the complex numbers. And then we also have the quaternions. They're represented by H because they were developed by Hamilton. And if we look at what a quaternion looks like, it looks like A plus BI plus CJ plus DK. Or, yes, DK. And I, J, and K play the same role as I does in complex numbers. A, B, C, and D here are real numbers. So I think it's good to spend a little while thinking about what the ordinals are. They're rather confusing. Most people have to spend a lot of time to sort of really understand what they are and how they work. But they're very useful. They're even useful in computing. So let me give you an example. So we'll go back to our whiteboard here. And we can think of, we have 0, 1, 2, 3. These are the finite ordinals. And if we take something like 2, 2 allows us to order two things. So let's say A and B, or plus and times. And basically the way we're going to order these two things is we're going to associate 0 with this and 1 with this. Now let's say I wanted to order an infinite number of things. I need an ordinal to do that, and this ordinal is called omega. And if I have an infinite number of things, let's say 0, 1, 2, 3. Oh, actually, I have a better idea. Let's say we have an infinite number of things, and we have 0, 1/2, 3 quarters, 7/8, 15/16, and so forth. So we can order these, and we associate 1 with the first, 0 with the first, 1 with the second, and so forth, like we did up here with 2. Now, omega denotes this. Omega is an ordinal that denotes how we've ordered this. But now let's look at another interesting case. So I have the real numbers like this, just like we had before. But I'm going to have all those infinite number. Then I'm going to start with 1, and we're going to have 1 1/2, 1 3/4, and so forth. So basically this is like 0, 1, 2, and 3. And then we start again, 0, 1, 2, so forth. And this number, this ordinal number, is omega plus omega. So if we were ordering this set of real numbers, they are ordered, the name for how they're ordered is this number, omega plus omega. Okay, so that's a really quick introduction to ordinals. Notice that the natural numbers are a subset of ordinals here. And the real numbers are a subset of the hyperreals. Actually, there are many sets of hyperreals. It's not a unique thing. We already talked about the bound thing. We haven't talked yet about S. S represents the surreal numbers. The surreal numbers were invented by a very great mathematician, John Conway. We could spend a lot of time talking about him. Unfortunately, he died last spring from COVID-19. John Conway invented the surreal numbers, but one of the first expositions of what they were was a novel written by Donald Knuth. Knuth is well known for things like inventing tech, on which LaTeX is built. All the documents we use in this course use LaTeX, so they all owe their existence to Donald Knuth. Donald Knuth is a Turing Award winner, and he wrote a novel, and the novel is called How 2X Students Turned Onto Pure Mathematics and Found Total Happiness. So the surreal numbers are like, as you can see here, they include the ordinals. Let me first get rid of this. They include the ordinals. They also include the reals and hyperreals. If you think of the real numbers, the real numbers are an ordered field. the surreal numbers are, in some sense, the biggest ordered field. Every other ordered field is going to be a subfield of the surreal numbers. So the surreal numbers are interesting. They're one of their applications is to studying different kinds of games. That's why John Conway was interested in them. But they're really more of a curiosity for computing. Same way with the quaternions. Quaternions were originally developed for doing calculations in three-dimensional space, but they're mostly a curiosity now. Okay, so what we're going to do is show you a table of number systems. These are the well-known systems and the other systems I mentioned. So here's the table of all the systems I mentioned. You can see on the left here, or right here, you can see we have classified them according to what kind of algebraic structures they are. And all of these are mathematical structures. They all have an addition and a multiplication, but they have different properties. So if we take something like the natural numbers, it is a semi-ring because if you look at the natural numbers with addition, we don't have an inverse operation. That's because we don't have the negative integers with us. Once you have the integers, you get a ring. With the rationals, you get an ordered field. With the reals, you get a complete ordered field. In fact, there is only one complete ordered field up to isomorphism, and that's the reals. With the complex numbers, we have an algebraically closed field. With the modular integers, if n is not prime, we have a ring that's not a field, and if n is prime, we have a field. The ordinals are a near semi-ring. This is because addition and multiplication are not commutative. I've already mentioned that the hyperreals are an ordered field, and the Gaussian integers are a ring. The Gaussian rationals are a field. The quaternions are almost a field, except multiplication is not commutative, so it's just a division ring. And S, the surreals, are an ordered field. Like I said, in some sense, the biggest ordered field. So we have all these number systems. How do we represent these in a computer? Well, there's different ways of doing it, and probably the four real basic systems are here. The first one is fixed precision integers. The way these are represented is we take a fixed number of bits. In this case, we take 2 to the n bits. Usually it's a power of 2, something like 16, 32, 64. We take that number of bits and we represent integers, both negative and positive. And this is usually done using the 2's complement approach. The 2's complement, the virtue of it is that we don't use a bit to represent negative or positive. The problem with that is then we would have two representations of 0. We'd have the negative 0 and positive 0. And we implement these fixed precision integers using modular arithmetic. So we basically get this kind of structure. We get the modular numbers where n in this case is 2 to the 2 to the n. It's 2 to the 2 to the n because we're using 2 to the n bits, and that gives us 2 to the 2 to the n possible numbers. So we're representing just a finite set of integers. What's good about this is we can do computation very fast. What's bad about this is if we have two big numbers in this set and we add them, we're not going to get the right answer. We're going to get the answer according to modular arithmetic. And that is something one has to keep track of. Now, fixed precision integers are for representing integers. If we want to represent rational numbers, we can use floating point numbers. With floating point numbers, again, we have a fixed number of bits, which is a power of 2. But we represent these numbers using scientific notation in base 2, something like this. And usually we have 1 bit for whether it's plus or minus, a certain number of bits for A here, and a certain number of bits for B. And then we also have to represent things like positive and negative affinity. We have to represent 0 in some way. Notice 0 does not have this form. And those are the floating point numbers. We're using a fixed number of bits. We can only represent a finite number of rational numbers, but this representation is very, very fast. But we can run into problems. We can have overflow. We can have numbers that are too big to represent, because when we do arithmetic with floating point numbers, the answers we get will always be approximate. We may not have a floating point number for the answer, so we take the closest floating point number. We can also get overflow. We could have a number that is always positive, like let's say we take 2, and we take any number and we divide it by 2, and we keep dividing it by 2. That will always remain. If we start with a positive number, that will always be positive. But with floating point numbers, at some point we'll have underflow, and that number will become 0. It'll go from being positive to 0, because 0 will become the best approximation. Now we can also represent integers and rational numbers using what's called arbitrary precision. This means, arbitrary precision means there's no limit on how many bits we can use to represent integers. So in a sense, we can represent integers exactly. We can represent every possible integer, no matter how big. If integers are too big, we may not be able to store them on our computer, but we can represent them in this scheme, no matter how big they are. And this is known as big nums. And similarly, we can have arbitrary precision rational numbers. We do this by taking 2 big nums. The 2 big nums represent a quotient of integers. Now, arbitrary precision integers and rational numbers are very nice because we can represent integers and rational numbers precisely, but they have a tremendous weakness. When we do computation, the computation is can be very slow, so slow we can't actually get the job done. So you see we have a tension here between fixed precision and arbitrary precision. Okay, well, we're going to stop here. We will continue next time with looking at some more mathematical values.